So, good morning, all of you. So, today we are at the third day of our faculty development program on emerging topics in computing, quantum, microfluidics, and memristors. So, today our entire day, the track will remain microfluidics. So, in this track, the first session will be delivered by the speaker, Dr. Tapolina Banerjee, and she will talk about the sample preparation with microfluidic biochips. Tapalina Banerjee is associate, an assistant professor in the Department of Computer Science and Engineering at JIS University, Kolkata. Earlier, she worked as assistant professor at Haldia Institute of Technology, Haldia. She has successfully completed PhD in technology, MTech, BTech, and BSc with honors, all from University of Calcutta in computer science and engineering. She did her research work at Indian Statistical Institute, Kolkata, as a Council of Scientific and Industrial Research (CSIR) Senior Research Fellowship grant from Human Resource Development Group, Government of India, and Project Linked Junior Research Fellowship grant from Indo-Taiwan Research Project from Science and Engineering Research Board, ACRB, Department of Science and Technology, DST, Government of India. She has published several papers in reputed journals and top-tier conferences. Her current research interests include microfluidic biochips-based algorithmic sample preparation, application in drug delivery, chip size optimization, security, and fault testing. She is keenly interested in dance, visual arts, and music. Before the age of 18, she has also completed Sangeet Visharat in Kathak, bachelor degree in music from Prachin Kalakendra, Chhattisgarh, Sangeet Sri in Rabindra Nritya from Bangyo Sangeet Parishad, and Charukala Sri in visual arts from Academy of Music and Fine Arts. So now I request Dr. Banerjee to please continue your session and share with us your knowledge. Thank you.
Thank you, Dr. Kole, for the nice introduction. Hopefully, I am audible.
Yes, ma'am, you are
Yes,
audible.
you are.
Thank you. Now, please let me know whether my screen is visible or not.
Now it is visible.
Okay. Fine. Is it properly visible?
Yes.
Okay, thank you. So, I am going to inform you regarding some basic knowledge of microfluidics along with how sample preparation is possible with microfluidic biochips. In the test tube era, automation, integration, miniaturization, all are absent. But then comes the era of robotics. Robotics comes with automation and integration, but miniaturization still absent. With the invent of microfluidics, all these three properties are there in a single device. Microfluidic lab on chips have fueled the automation of biochemical protocols on a tiny device. These devices enable the movement of microliter, nanoliter, even picoliter volume of fluids through microchannels or on patterned array of electrodes as discrete droplets. Now, skilled technicians of a pathological laboratory handle different complex operations by using bulky set of instruments. Now this whole path lab is integrated on a tiny lab on chip. We call
You are not audible.
I think there is some network issue.
Okay.
am I now audible? Maybe some network issue was there,
Yes,
right?
yes, yes. You are audible
Okay,
right now. Yes, yes.
okay. So how long you have heard about this part?
Ma'am, please go to the slideshow view actually.
Yes, yes.
You can start from the beginning of this part. Actually, you
Okay,
started and we were not able to hear anything.
okay, okay, ma'am. Fine. So, in our real life, whenever we are considering a lab-based protocols, then skilled technicians of pathological laboratory have the capability to handle different complex operations. And these things are possible by using bulky equipments, right? But with the invent of microfluidics lab on chip, this whole path lab is possible to integrate on a tiny LOC. And this is known as path lab on chip. Biochips provide first and low-cost solution to various applications such as sample preparation, pathological diagnostics, DNA analysis, shell sorting, drug design, and synthetic biology. Microfluidic technology has the potential of replacing conventional benchtop protocols by combining the functionalities of biochemical analysis with sensors on a single chip. Now, we can see that microfluidic lab on chip based systems can perform a variety of tasks, right? Such as mixing, separating, detecting molecules, analyze substances, etc. etc. Thus, these devices have a potentially enormous impact in application areas of physics, chemistry, medicine, biology, as well as in pharmaceuticals. Non-traditional applications of microfluidics are also notable. These include material synthesis, energy harvesting, microfluidic cooling, microfluidic logic, display, images, and sensing. Applications of different lab on chips are available from the collecting samples at the area of crime scenes for DNA analysis to disposal entry card like this. So basically, these four characteristics, higher throughput and sensitivity of a lab on chip, minimum intervention, small requirement of costly sample or reagent, and overall the low cost help the microfluidic lab on chip become popular in all these fields. So researchers from the arena of microfluidics and biology have published numerous articles on the impact of microfluidic sample preparation gradient generators with versatile biochemical applications. Now, advances in microfluidic technologies over the last few decades have led to the development of lab-on-chip devices that provide a multitude of fluidic functions on a single chip. They are increasingly replacing bulky and expensive biochemical benchtop procedures needed in hospitals, research labs, or at point of care stations. Now, two major classes of LOCs are primarily used in practice. One of these is digital microfluidic biochip and another one is continuous flow microfluidic biochip. In CFMB or continuous flow microfluidic biochip, here permanently etched microchannels with presence of micropumps, microvalves, etc. are handled. In case of digital microfluidic, discrete droplet manipulations are done by using what? By using a patterned array of electrodes. Further, if we want to classify this CFMB, it can be of two types. One is valve-based. In the present era of biochips, more than 25,000 microvalves are used to implement large-scale and concurrent experiments. And another one is free-flowing. Free-flowing of fluids through rigid microchannels network are of concern. Now, this both CFMB and DMFB, both this type have another common classification known as segmented flow or microfluidic network on chip. While several computer-aided design or CAD tools have already been developed for DMFB, very few available for this CFMB. CFMBs are historically more preferred where in the biochemistry community to implement various assays and detection. Now, we can see that microfluidic devices have found various applications in the field of biochemical research, biomedical diagnosis, food industries, etc., etc. This emerging technology provides automation, miniaturization, and integration that we have already discussed. So, one of the essential components in the biochemical analysis is fluid sample preparation, which involves the preparation of dilution and or a mixture of several fluids in a certain ratio. Several sample preparation techniques based on this continuous flow microfluidic biochip technology appeared in different literature and also based on digital microfluidic biochip technology. Fine. Now, recently, various implementation of a wide range of bioprotocols, including error correction and sample preparation on handheld devices using microelectrode dot array technology have emerged. So, let's take a look into some physical structure of these microfluidic devices. In general, you can see that here we have schematic view of two-layer flow-based microfluidic device. In our left-hand side, we have a top view and right-hand side, we have the cross-sectional view. In general, continuous flow microfluidic biochip is furnished with a number of pressure-driven microvalves. Those are responsible for controlling fluid flow through a network. Okay. Network of what? Network of microchannels. So CFMB devices consist of two separate layers. One is control layer and another is flow layer. Fine. Now, these devices consist of two separate layers of elastomer, polydimethyl siloxane or PDMS, based flow layer as well as control layer. Okay. So the network of microchannels in both of these two layers are fabricated by using soft lithographic techniques. Microchannels in both layers are also connected by an external pressure source. The current technology of microfluidic large-scale integration, or in short MLSI, enables CFMBs to fabricate thousands of microvalves on a single chip. A flexible microvalve, or you can say the membrane, which controls the area between the channels of two layers, or which controls the movement of biochemical fluids in the flow layer, is mainly constructed by what? At the overlapping area between these two. Fine. Now, fluidic flow is blocked. How? Fluidic flow is blocked when corresponding microvalve is deflected deep into the flow channels by an external pressure. Okay, so this external pressure is obviously going to be held in the control layer. Based on these microvalve operations, many fluidic primitives can be implemented on chip. Fluidic primitives mean what? Such as rotary mixers, switches, multiplexer, pump, etc. etc. The movement of fluids in microfluidic channels hence can be managed by organizing these microvalves as switches to establish what? To establish the desired flow path. So, switches are used to restrict or to allow fluid flow in a microchannel depending on the condition of the valve or the state of the valve. If valve is closed, then restricted flow. If valve is open, then allow the flow. These are the simple things. Now, here we can see that this is a very simple view of digital microfluidic biochip. This manipulates once again the nanoliter, picoliter volume of droplets. You can notice that this structure, this is just like a simple 2D array, right? But this 2D array is consists of mainly electrodes, or we can say 2D array of electrodes using the phenomena electroweighting on dielectric. Fine. Another case, which is microelectrode dot array, or in short, it is called as MEDA. This MEDA-based DMFBs provide an extension of this concept of DMFB. Okay, and this MEDA allows for higher granularity or resolution and more flexible operations compared to conventional DMFBs. In both of these cases, you can see there is two layers, two interfaces. One is microfluidic interface and electronic interface in case of DMFB, and in case of MEDA, along with microfluidic interface, it consists of microelectronic interface. Okay, so it contains two plates similar to conventional DMFBs. A top plate which acts as a reference electrode and a bottom plate with patterned microelectrodes with integrated capacitive sensors. A dielectric layer and a hydrophobic layer are generally placed on top of microelectrode interface. Droplets are sandwiched between the top plate and bottom plate and transported by applying what? By applying appropriate voltage. You can see voltage application is possible in this way. So applying the appropriate voltage to the neighboring electrodes. A set of microelectrodes forms a functional electrode. Here it is. Okay, we can see that single electrode now going to be treated as a set of microelectrodes. A set of microelectrodes forms a functional electrode and high voltages are applied to them in order to perform certain fluidic operations. In Mader-based DMFPs, silicon oil is generally put between two plates, top and bottom. And it is treated as what? As a filler medium to prevent droplet evaporation. Okay. Now, one more thing that we have to notice that MEDA allows fractional aliquoting of droplets, that is of varying volumes. Okay, this is highlighting by comparing using this blue color mark. So, MEDA allows fractional aliquoting of droplets in a fine-grained manner compared to conventional DMFPs, where the droplet volume is fixed. So, aliquoting with MEDA chips has been recently used for error recovery and for mixture preparation while exploring parameter space in the context of synthetic biology. So due to architectural flexibility, MEDA biochips can perform some advanced microfluidic operations such as channel dispensing, fluid merging operation, etc., which are not possible in the traditional DMFPs without errors. So MEDA can preciously dispense a certain amount of fluid using channel dispensing operations. Now, we need to look into some physical channel structures. One of the most important challenges in continuous flow microfluidic biochip is to perform homogeneous mixing of fluids. Physical design, especially the geometry of the micromixer channels, plays a vital role in the designing of the mixture. Here you can see a Christmas tree-shaped fluidic network served as sample pressure-driven microfluidic gradient generator systems. The big footprint and the high fluid injection pressure make the tree-shaped fluidic networks impractical at large order. You can notice that from these two inlets, we can inject the fluids. With this spatial network structure, just like a Christmas tree-like structure, mixing can be possible and a fixed ratio of gradients we can receive at the outlet part. Fine. Next one. Here, another view. A modified fluidic network is used to generate the same number of concentration, just like the previous Christmas tree. You can see here it is 1, 2, 3, 4, 5. 5 output. Here we are going to have the same number of output with expecting the same ratio of gradients, concentrations ratios, but with fewer stages, right? Fewer stages compared to traditional tree-shaped fluidic networks. Although the basic principle of these two designs are almost same, they differ in splitting protocols. Both of them consume large volumes of costly samples. Okay, now this is another shape of a network that we can use, another physical channel structure. An improved fluidic network comprising Y-shaped junctions obviates this problem through suffers from shearing. Okay, But after this, what T-shaped? A convention-based gradient generator based on T-shaped channel was also used to investigate cell responses. Here, the direction of arrows can be identified easily that these are the input direction, these are the mixing channel, and here we are going to get the output. Output of a resultant mixing volume of fluid, resultant mixing fluids or diluted fluid. At next, the planar flow focusing mixture is a special form of Y-shaped network. Okay. So here more than 3 inlets are come out and joined and then mixed. It is possible that this one is another outlet part may be connected here as an inlet of this one, and so on so forth, as per the requirement or as per the proposed architecture. Now this is another cross-shift planar flow focusing mixture. Now, mixing based on chaotic advection can be achieved using this type of structure. This is known as Tesla structure. Homogeneous mixing of fluids can often be accomplished in flow-based biochips by alternating chaotic splitting and recombinations. A mixer can be designed by combining the effect of what? Effect of split and recombination using pattern groups such as here we can see the herringbone structure. Okay. So serpentine mixture, microchannels with pattern groups, herringbone, staggered herringbone mixtures, in short SHM, belong to this type of split and recombination characteristics wise architecture or physical channel structure. Now, here we can see valve-based continuous flow microfluidic chips equipped with in-segment rotary mixture. Okay, here it is. You can see these are the ratio valves, these are the pumping valves. Here we can see these are treated as inlet as well as outlets based on the condition or the requirement of our resultant fluid or diluted fluid. So our satisfiability based algorithm is deployed there to obtain an optimal mixing graph. Okay. Now here using this pumping valve and the ratio valves, we can mix suppose 2:3:1 or 2:2, different types of amount of fluids can be mixed with the different ratios. We will learn very shortly about this mixing of ratios and all those stuffs. Field programmable valve array. This is another interesting physical channel structure. These are also used in continuous flow microfluidic biology. You can notice that there is a mux controlling set where pressure inputs are given, and based on the latched output, different intermediate valves, or you can say the core valves, are either activated or deactivated to channelize the particular path of the fluid flow. Now, another thing, valve-based 2D grid type continuous flow microfluidic biochips. These offer the advantage of programmability for sample preparation. This advantage we also receive from this FPGA, the programmability. For example, if we consider this valve-based grid of 2 input, 3 output, Then you can notice these are the input lines and these are the output channels. And here, these all dark circles are simply the valves. Same thing happen in case of 3 input and 5 output based valve based grid. Okay, these are the different 2D grid type CFMB's network. Now, any defect in elastic microvalves or micropumps may also introduce various microfluidic errors in this type of valve-based CFMBs. So this is obviously a drawback of this type of architecture. Now, there is a one-to-one correspondence between a hydraulic and its equivalent electrical circuit. Before that, we have described different types of physical channel structure, right? Now we are going to map and we are willing to see how this mapping is possible. Okay, let's see. In case of this hydraulic circuit, we can see we have a concept of fluid pressure. This fluid pressure is equivalent to the voltage of an electrical circuit or electric circuit. Volumetric flow rate of an fluidic or hydraulic circuit can be mapped as a current into the electric circuit. Similarly, hydraulic resistance is correlated with electrical resistance in its equivalent electrical network. So let's see this example. Okay, it will help us to analyze the behavior of a microfluidic channel network. Okay, let's see. Here we have considered this Y-shaped rigid microchannel. Okay, now this through source inlets A and B, two miscible fluids are injected with volumetric flow rate, suppose QA and QB. Now, fluids meet at junction X and flow towards sink outlet C without, why we can see this is the sink outlet C and the output at the outlet, the volumetric flow rate is QC. So source inlet arms AX and BX. These are source inlet arms and we are considering that these are of same dimensions. Now, this XC is the mixer part. As a part electric hydraulic analogy, this fluid flow, source inlet, sink or drain outlet, fluid flow source, pressure source, hydraulic resistance, volumetric flow rate, all are can be replaced using this simple electric circuit. Okay. And in this case, all these are going to be converted as electric current, input terminal, output terminal. If we mapped it individually, then it will look like fluid flow into form of electric current. Source inlet into form of input terminal. Drain outlet or sink outlet going to be treated as output terminal. Fluid flow source now become current source, voltage source.
I'm just interrupting. What is this RMX?
This one, actually this is the resistance of this XC mixing part. We can treat it as the hydraulic resistance in this mixture channel.
So the fluids are moving through these channels through these resistances.
Yes. So see, if we are going to change the width, the height, then obviously it will affect the resistance, right?
Yes.
And this will change the fluid flow rate And also, whenever there are different types of mixing pattern at the mixing channel, then there is a possibility of different mixing ratios also based on this hydraulic resistance. Right?
Okay.
Oh, thank you. So, in this way, we can map the fluidic network into its equivalent electrical network. So, here we can see one parametric analogy between a fluidic and an electrical network. Here, at the left hand side, we have considered most of the electronics physical properties, and the corresponding microfluidic properties are in our right hand side along with the unit. So you can see that KCL, KVL, which are applicable in our electronic circuit, are also able to get application in our microfluidics because of this similarity. So the equivalent resistor for series connection can be calculated in our microfluidics process. How? Equivalent fluidic resistance like thing. Okay, it may be of series connection, may be of parallel connection, etc. etc. Now, basics of flow dynamics. Few equations that are required to know about the basics of flow dynamics. It will help us to understand how whenever we are trying to make some or we are going to propose some fluidic network, then this should be taken care of. In CFMBs, let me get the pen. Okay, fine. So here we are going to start with this Reynolds number. Reynolds number is what? It is simply a dimensionless parameter used to characterize the nature of fluid motion. Fine. Now, Reynolds number should be constantly lower than 2300 so that it will ensure that whether laminar flow is there or not in our fluidic network. So here is the concept of Reynolds number calculating part. It is simply the ratio of inertial force versus the viscous force, where we can see if we convert it into this form, then this rho is simply the density of fluid. Mu is going to be treated as fluid dynamics viscosity. This nu is fluid kinematic viscosity. L stands for fluidic channel length, and U stands the speed of fluid flow. A high value of R indicates high value of this Reynolds number R indicates turbulent flow, whereas low value indicates the presence of laminar flow in the network. Next come the Navier-Stokes equations. These all are very popular physics equations, but I am willing to show all these equations at a glance so that whenever flow dynamics are of our concern, we can aware about this all. The Navier-Stokes equation governs the motion of fluids, and this is analogous to Newton's second law of motion for fluids. In the case of incompressible Newtonian fluid, this equation must be hold, where we can see that all this U is already known as fluid velocity. New one is P. P is the fluid pressure. And other that rho, mu, these are just like the same as Reynolds number. Now, this one, the left hand side term represent inertial forces. And whenever we are considering the right hand side, the term this minus del P or this represents pressure force. And this one is going to be represent what? Simply the viscous force. And F is denoted the external forces applied to the fluid. The equation are solved together with this continuity equation. Fine. Now, the two properties mainly named as conservation of momentum. So, conservation of momentum for incompressible fluids are captured by Navier-Stokes equation, and the conservation of mass for incompressible fluids are captured by this continuity equation. The relative concentration of sample is represented by Fick's law. Using Fick's laws, one can find the solution of the convection diffusion equation. Okay, in our area, we have used this equation lots of time. Okay, and there exists this advection. Okay, now here we can see that new term DI. DI is diffusion coefficient of fluid I in the solution. The conserved the conserved quantity Ci, this one is the concentration of the fluid I, and this R is not the Reynolds number. This one is the reaction rate of the fluids. Next comes the Refuter's equation. The fluid kinematic viscosity nu of a mixture of two or more miscible fluids can be estimated by Refuter's equation. These are the combinations. So I am not going into the details of all this, but just need to know that one can use electric hydraulic analogy to estimate the hydraulic resistance in the fluid network and equate laminar flow through a channel network with current flowing in the equivalent electric network. And Refuter's equation can help to identify that one. Next comes the HP law or Hagen-Poiseuille law. In this case, what we have, we can found that this HP law is a physical law that relates the pressure drop in a fluid flow through a long pipe with its volumetric flow rate. Three underlying assumptions have to be taken here. First of all, liquid flows through a tube of constant cross-section. Flow must be laminar and fluid should be Newtonian fluid. Hence, according to HP law, the volumetric fluid flow rate Q become this one, where del P is simply the pressure drop between source inlet and the sink outlet. R stands for the fluidic channel radius and L for the fluidic channel length, and mu, just like previous thing, dynamic viscosity of the fluid. Now, if we are going to consider the hydraulic resistance of a channel with circular or rectangular cross section, then these two equations play one very important role. First of all, the analog of Ohm's law of current, which all of we know that V equal IR means voltage drop equals to current cross resistance. Now, if we map these things into the fluid mechanics, it is treated as pressure drop equal to fluid flow rate into fluidic resistance. Based on that, in circular conducts, hydraulic resistance, this R hydraulic, can be represented as like this. And similarly, in case of fluid flow, if fluid flow going through this rectangular tube, then hydraulic resistance will be calculated just like this formula. So these are very much useful to construct an equivalent electrical circuit model for a microfluidic network of channels. Now we are in the process of sample processing. I have used this term sample preparation lots of time. Now I am willing to show you how these things are happened with an example in our microfluidic area. See, in case of biochemical laboratory, sample collection, then measurement, then the dilution, mixing, storage, all these stages are very much required, right? Now, is it possible to implement dilution and mixing all these things on a tiny lab on chip where sample collection, measurement, dilution, mixing, storage, everything is possible? Yes, it is possible. See, one of the essential factors in biochemical analysis is pre-processing of fluid samples, which involves preparation of dilution and or mixture of several fluids in a certain ratio. Several sample preparation techniques based on continuous flow microfluidic biochip based algorithmic sample preparation is possible, as well as using algorithmic sample preparation with digital microfluidics. So, algorithmic sample preparation with LOCs requires determination of a sequence of mix split operations to be performed on two or more fluidic reagents. For dilution of a sample, it is mixed with buffer fluids in a given volumetric ratio to achieve a desired target concentration factor of a sample. And in case of fluid mixture preparation, mixing is occur between more than two miscible fluids in a certain ratio. Let's have a look of use of sample preparation in drug design. Dilution gradients plays an important role in the determination of the minimum amount of an antibiotic that inhibits the visible growth of bacteria isolate. COVID-19 has initiated a race of drug design to tackle the continuous spreading of novel coronavirus and other human respiratory viral infections. Microfluidic biochips are heavily used in this type of drug design. It could play a vital role for point of care testing for early diagnosis of suspected cases and treatment monitoring of infected people to prevent what? Prevent further spread of the infection. Now, if we are considering the dilution and mixing based on this algorithmic sample preparation knowledge, then what we can see? Here we are going to consider a fluid F with volume V and the concentration C1. Another fluid, the same fluid F with volume V but with other concentration C2. Fine. Now, if we want to make a 1:1 mix model, then what will be the outcome concentration of the fluid that are going to be treated as a resultant of 1:1 mix model? It should be this mean value of two concentrations. Okay. Now, same thing can happen if we are considering digital microfluidics. In this case, 1:1 mixing, you can see one volume of droplet of concentration C1 is going to be mixed with concentration C2 based one volume once again. Another volume is also 1. So 2V is the resultant volume with C1 plus C2 by 2 resultant concentration. Now, if we split it, then we may have two volume of droplets, each of one volume if there is no error. We are considering here there is no error. So each of these volume is of C1 plus C2 by 2 concentration. Now, droplets are available only as integral quantity. And in case of mixing, splitting, balancing is very much required. This is another simple view when we are considering one of the fluid as sample and another fluid is buffer. So considering this sample concentration as C and buffer concentration as 0, the diluted sample concentration becomes C by 2. So after 1:1 mix split, we have two droplets, each of one volume, but concentration is C by 2. We can notice that the denominator is 2. So if we are considering this resultant volume and mixed with another same volume droplet of buffer, then split it, then the outcome will be C by 2 to the power 2 and so on so forth. Now, let us consider few different volumetric mixing or dilution models. This one we have already learned. This 1:1 mixing between two fluids, either same or different sample, can generate the resultant fluid as this concentration. But if we consider that X:Y mixing between two fluids, either same or different samples, then the resultant concentration have to be calculated in this way. This XC1 plus YC2 by 2. Now, if one of the sample is one of the fluid is raw sample and another one is neutral buffer, then in case of 1:1 mixing, we have this one as our resultant concentration. And same thing if happen between X:Y dilution model, then the concentration factor should be look like this. XCS by X plus Y. Now, if we generalize this thing, that we are going to mix with X1 is to X2 is to dot 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 up to XM mixing among more than two fluids, then the outcome is look like this. This is the resultant concentration fluid after mixing these fluids of these volumes, ratio volumes. So if one of them is now become the neutral buffer and others are different miscible fluids, then the resultant concentration values will be calculated in this form. So if we are using dilution using flow-based tubes, then there are obviously valve-based tubes as well as there is free-flowing tubes. So in case of valve-based tubes, non-reliability is there. Okay. In case of free-flowing tubes, non-programmability is there in most of the cases. Even achievement of fine accuracy of concentration factor is very hard in case of free-flowing tubes compared to the digital microfluidic. Now, whenever there is splitting means we are incurring the volumetric error also. Fine. So, this will render the outcome of the assay erroneous. Now, we can take this type of challenges whenever we are willing to propose some special network design for sample preparation using continuous flow. First of all, we need to take care of programmability, robustness. These things are very much important. If we are taking these things as our challenge and able to make free-flowing chips for algorithmic sample preparation, it is really good. And we have done few of these things. Achieve of high accuracy in CFMB similar to that in DMFB is also a very much challenge. Now, here are few constraints that I have jotted down here. We can take care of all this, even there may be, we can include few more in future also. So, at most two metering means two different types of fluid injections, speed or something like this. We need to avoid the splitting as much as possible so that volumetric error can be avoided. If we are trying to make the valve free or control layer free, then it will obviously help a lot on designing online chip. Sustainability of resultant concentration factor in the target fuel have to be guaranteed. And at the end, laminar flow through microchannels must be ensured. Now, if we consider dilution using DFMBs, then the existing methods mostly suffer with these possibilities. That it requires sensing while producing the target CFs, intermediate droplet sharing is required while multiple dilution of sample is done in parallelized fashion. Now, if you can see here, the splitting is there. Different types of volumetric errors is there. If 1:1's balance split occur, then fine. But if unbalanced occur at the end of splitting, when 1:1 unbalanced splitting is there, then you can see different volumes. So obviously, this will propagate to the next layer when these droplets are going to be used. And here, we can see a small residue is there, the imperfect split. Okay, so we have to take care all of these and makes a set of challenges to overcome this, such as design of programmable and robust nature-based DFMVs for reliable sample preparation, as well as conveniently implement on microelectrode dot additives. Now, in this case, whenever we are going to handle the meta chips, then allocating and mix operation that allows the precise manipulation of what? Of our fractional volume droplets. It should be treated as one important constraint. Now, since time permit, we can continue to see two different problems, how we have solved this. First of all, the motivation behind the first problem. W. Thies and their group first proposed a mixing algorithm based on bit scanning algorithm or two-way mix algorithm, TWM method. Dilution is a special case of mixing where a sample is mixed with a buffer in a certain ratio. To implement dilution, the given target concentration factor is first approximated with the user-defined n bit. Okay, now we can see if our target is 30% target CF with n as 10, then we can write it in this way, 313 by 1024. This 1024 is nothing but simply 2 to the power n by 2 to the power 10. Now, if we consider the making of binary equivalent of this value, it should be like this. Okay, so here n is a positive integer that determines the maximum allowable error in CF. Fine. CF means concentration factor. Now, mixing is performed based on the 1:1 model, where 1 unit of sample is mixed with 1 unit of buffer and only 1 unit of the resulting mixture is used, discarding the remaining unit as waste. Okay, let's see how it is possible. The two-way mix, the two-way mix algorithm works on scanning the bits of the binary fraction from right to left to decide whether a droplet of sample or a buffer is to be used to mix with 1 unit of fluid that was produced at the preceding step. So if we find it's 1, we have to use this sample droplet. If it is 0, then we have to use the buffer droplet. Okay, thus except the last step where 2 units of fluid with target concentration factor are obtained, 1 fluid unit is wasted at each mix split step. This algorithm requires the minimum number of 1:1 mix split steps needed to produce a target concentration with accuracy level N as mentioned with the problem, where reuse of waste droplet is not performed. Fine. Now let's see how this can be possible. Fine. This is our input direction and the scan bit is going to be start from right to left. It is 1. Since this is the first one, we have to take 1 droplet of sample as well as 1 droplet of buffer. So the resultant is this one. Simply 1024 plus 0 by 2, this is 512. And the denominator becomes same. Now next scan bit is 0. So which one we need to add? 1 droplet from buffer. Fine. You can notice that this is the waste droplet because we are going to make 1:1 mix split. So mixing of these two 1 unit will produce 2 volume. So we are processed with 1 volume and we are wasting 1 volume parallelly. And this thing happen at each mix split stage. Now 0, it means once again we need to mix with another buffer droplet. This is 1 means mixing is required with 1 unit volume of sample droplet. So on so forth, we will receive our target. Now 2 droplets of target CF is there, right? Along with, if we calculated these values, the number of buffer solution droplet used is 6. You can notice 1, 2, 3, 4. Sorry, this one. 1, 2, 3, 4, 5, 6. This is 6 buffer droplet used. Whereas sample droplet used as number of 5. 1, 2, 3, 4, 5. And waste occurred as each stage, except the last one where 2 droplets are produced. Now, so if we want to implement this concept in our continuous flow, then what are the challenges that we have faced? We have faced these challenges that at first application of this well-known BS method in DFMB is CFMB with proper modifications. We want to make it programmable without using control valve. Next, we want to avoid this splitting part. Our target is to avoid this volumetric error. Fine. So splitless mixing is going to be take part as our network. Now, wastage, sample wastage is not acceptable because sample is very costly. So design of generalized fluidic network for any target CF in the form of this, we want to make it as waste free also. Fine. Next one is fluid injection timing. We want to make it predefined. And this predefinition will be irrespective of the target CF. Mixing channels, we want to make it free of microvalves. As well as we have simulated this network where all these challenges overcome using the COMSOL multiphysics software. So finally, this is the problem description. So in our problem description, what we did, a supply of sample fluid there, which is considered as 100% concentration or CFS1, and we have buffer fluid, which is considered as 0% concentration, that is CFS0. Along with this, we are going to consider one positive integer n denoting the accuracy level. Okay, this should be given from the user side. A mix sequence that will generate the target concentration CF, which is known as TCF, must not exceed this allowable error plus minus 1 by 2 to the power n plus 1. So let's see, based on this, how we can perform to make such an CFMB. At first, take a quick look into our fluidic network represented as electrical circuit, where flow rate towards each junctions is there, and here is the relation between each fluidic resistance and the fluidic flow rate. So based on these two, we are mostly based on these two equations, that hydraulic resistance of the microchannel combining HP flow and Ohm's law, we have this one, and we know that Reynolds number is this one, right? So considering all these, we are able to implement one hydraulic circuit or the network. We propose a continuous flow fluidic network for implementing the dilution algorithm, where each inlet will have a predetermined cross-section and fluid injection velocity regardless of the target CF. Please note, these are regardless of the target CF. So any kind of target CF can be achieved. We need not to change the structure for it. Previously, in case of that Christmas tree-like structure and all those stuff, at the output, we are receiving a fixed concentration ratios. But now we have overcome from this problem. We consider two types of geometry. Let us consider this first one. Here you can see this is the input direction. All these points are inlets, and in between these we have this microchannel. Dimensions are specified also here. But the thing is, the number of Y-shaped serpentine microchannels that we have used is similarly the number of binary bit representation of the concentration factor. So it is simply N. And next one is, this mixing is possible by convective diffusive transport through fluidic network. Okay. Now, in another model, we can see that in this case, need to back one more here. In this case, the speed in which we have injected the fluid through the inlets have to be geometrically increased one by one, and the increment factor is 2. But to make the injection flow rate,
Madam, I'm just interrupting once.
Yes,
So
yes.
I just wanted to ask, suppose this is 25 micrometer, this is 200 micrometer. Is it the same for all the tests, or it is specific to some test? Is it like this?
Actually, this is for this particular structure. Okay, so if we are doing some other kind of structure, other kind of network, then it's depend on how the convective diffusion is occur, what is the resultant hydraulic resistance that we want in that channel. Depend on that, we have to choose the proper dimensions.
Okay, and one more thing, suppose a few tests will be conducted here, but not all
Yes.
tests, right?
Okay.
That is what I'm asking. Is it
Yes,
that?
yes. A set of tests of we have tested through this microfluidic, through this console multiphysics. Okay, simulation based. So
Okay.
few tests we have performed, and they all of them are sound good.
Okay. Okay.
I will show you the results also.
Okay.
So now we are going to change that the number of injection that we are going to inject the fluid flow rate become some changes there. Not so much different fluid injection rates are going to be handled. How we can reduce it? By using these simple changes. Okay. Now we use special rectangular boxes to augment the inlets as shown here. Okay, we choose channel dimensions and fluid injection velocities following certain rules and study the flow dynamics in 2D for different input concentration profiles using COMSOL multiphysics software. Now, you can notice that if we are A and B is this one, A, B, C, D and all this stuff, these are the inlets and these are the inlet width in micrometer. Fine. Now, this will change the requirement of different fluid injection velocities at each stage. Now, only you can see using two applied velocity at inlet boundary, we can achieve this number of different velocity by using this structure. Okay. So, these are a very simple tricks but helps a lot to change the applied velocity, or you can say to reduce the applied velocity in only this two. Whereas in the previous model, we need to inject with this number of different injection velocities of the fluid at each inlet. Now, this is the simulation framework where we can see that these are the very basic informations regarding CPU, operating system, software. Now, the main thing is we have used these three materials as well as we have chosen these two different physics, laminar flow and the transport of dilute species. Fine. Meshing is also an important one. We set it as an extra fine while calibrating the fluid dynamics. And this is the time dependent that we have tested. Now, if we want to, time is lacking, but still I want to go through this flow of COMSOL multiphysics simulation very quickly. See, at first we need to make the space dimension of the model, have to take the material characteristics from the material library available in the COMSOL multiphysics and need to set the other parameters of the model. Then we need to create the proper geometry of our flow model to support the flow layer physical design. Now, at next, material characteristics with the model have to be chosen accordingly. After that, we need to take the physics library. We need to take the proper physics or multiphysics with our model. So it is possible by the help of physics library. At next, we need to make the meshing properly. And this is help us to calibrate the proper fluid dynamics. After successful meshing, what we can do, if the meshing is not success, then we need to reset it once again. Otherwise, we can proceed for the boundary setup combination, combining input loads, output condition, etc. Now, at next, we need to set the time dependent study, and parallelly we need to configure the solver. So physics interface in study is also main concern at this stage, and all these things can be possible using the study library. After that, we need to compute the model. Then if solution is not right, then we have to check whether our study was right or not. If it is not, then we have to change the study set accordingly. But if study set is fine, but the boundary conditions and physics are not wrong, so we have to change it. Otherwise, we need to check whether there is some problem at the choice of material characteristics. If it is, then we have to modify accordingly. Otherwise, we start from the very beginning. But if we are getting our perfect solution, then we can proceed for the post-processing analysis. Now, in this case, for this particular model, we have set the injection time at each inlet just like this. So these are predefined. We need not to change it based on the target concentration factor. Okay, it is for all. Now here are we have reflecting only 4 results where we can see that all the results are of very few error. You can notice for the target CF 313, we have received this as our result. So error is only this one. This is very much challenging. To get such small amount of error in CFMB is really challenging and we able to do it. So in this way, this is a simulation. Let's see the video of the simulation that how this mixing is occurred. You can see the changes of color based on the concentration change. Okay. Now, at the conclusion, we can say that yes, now programmable method of continuous flow microfluidic network is possible. This was the first ever case that we have designed such programmable method, and this is irrespective of target CF. Any target CF can be implemented in it. Now, we can use only 2 fluid injection velocities and 5 different dimensions which help us effectively produce 10 different fluid injection velocities at the inlets of our proposed fluidic network. Okay. But time is not so much. Can I cover this 3D modeling of fluidic network?
Yes, you can take another 15 minutes. Is it okay?
Okay. That will be enough.
Okay.
Thank you. So, in case of this 3D modeling of fluidic network, we have to suppose that a 2D model of flow based of bead scanning algorithm already discussed. It is actually the chapter 3.1 for my thesis part. Actually, this is the previous one, which requires only sample and buffer as inputs. Now, we are next going to adopt the REMIA, reactant minimization algorithm, on a 3D free-flowing fluidic architecture, where we are going to use the PCVs. PCVs are simply prime concentration values, which are only simply the diluted form of the samples. And we can make our target concentration factor by using 2 independent steps. Let's see. So at first, challenges are simply like how we can apply this DMFB based REMIA into this CFMB. Okay, next one is obviously we need to take care the samples are very much costly. So as much as less we can use it, it will be good for the costliness. Now, simulation in real life 3D fluid dynamics also performed using once again the same software. Let's see how it is possible. In case of BS, if we are considering target CF as 95 by 256, then the equivalent binary form is this one. So in case of BS, we have this tree. Okay. But in case of REMIA, what we have? We have this How it is possible? This is the background theory of Remia, that how reactant minimization algorithm can change the use of these costly samples reduced in this PCVs. Okay, PCVs means what? If 256 sample is diluted into buffer, then it will consider to be as 128. Then if 128 concentration factor again diluted in buffer, then it will be changed into 64. Note that 1:1 mixing have to be considered in these cases. But you can see each of these stages we are going, in this case, we are going to have some waste droplets, right? Same thing happen in here. But in our continuous, we don't want to waste any fluid. Fine. So how we can make it? Let's see. Here is the model, where we can see that the same serpentine mixture of Y channels are going to be performed, but now in a 3D look. Okay, so in this case, what we can see, the same thing happen here to make the change of fluid injection velocity at each stage reduced into only 2 by changing these inlet dimensions. So here is once again, we want to set the injection time at each inlet junction irrespective of our target CF, and then this is the simulation framework. So here we have used water, ethanol, glycerol, these 3 compressible Newtonian fluids, and also use the physics laminar flow to get the single phase flow and transport of diluted species. Now, this one is the resultant view of our console view of the fluid flow in the channel. We told that our model describe what? Describe laminar flow. And we expecting that all proposed model regarding this continuous flow may maintain this one. So we need to show this, that whether laminar flow is there or not, because we are claiming that yes, Reynolds numbers is very much low as per the dimension of our structure that we have considered based on the basics of flow dynamics and all those stuff. So this is the reflection. Yes, this show that fluid flow is laminar throughout the channel. There is no turbulence. Now here is another view of the same mixing, where you can some problem there. You can see that after certain time, the stability of the output concentration reached. Let's see. Oh, okay. Just look at into it. At first, it will obviously not stable, but after some seconds, the concentration become stable. So stability at the output or the outlet channel is also very much required to ensure. Now this is another example where we compare these 2 methods, and we can see that within safe zone, these are belongs. Safe zones mean within the error boundary, that are allowable error. But the second one is less error. Fine. So obviously, whatever we are going to receive at our outlet with less error should be accepted. Here is a comparison where we can see these 3 papers where their methods are compared, and we can see the errors in their output concentration factor, and we can see that this one, the third one, this is what I am talking right now, is going to be achieve less error at each stage. Okay, so at conclusion, what we can say, this was the first ever programmable 3D simulation of continuous flow. Fine. So we can go forward with this type of thing. And also, since we have used the less use of costly sample compared to the earlier one, it will help us to reduce the cost also. So this type of challenges can be taken in case of continuous flow microfluidic and try to overcome it. This faster convergence and improved accuracy achieving of these two is very much challenging. Whenever we achieve this one, it is really a good direction of the research part. So what next can be done from this set? First of all, we can make target of interfacing with other flow-based platforms, as well as we can embed test and security issues in the microfluidic lab on chips while preparing the samples or simply the sample preparations. That's all. So any question?
Dear participants, please you may ask any questions if you have.
Okay, so I will ask a very simple question because I'm naive in this topic. So I'm curious to know a few things. Like when you do real testing on such
Yes.
chips,
Yes.
so there are many different challenges, right? Because approximating exact amount of certain chemicals into the blood samples and then mixing
Right.
it, and there are a lot of things. So
Yes.
uh, how accurate is these devices? So these devices have already been commercialized, right?
Hopefully. But first of all, I want to say that we have designed this type of devices right now using this simulation environment. And one of our proposed architecture is under this real life chip design. Fine. But apart from that, there are few chips which are available in the market. They have already designed in the real life lab and they're able to perform the similar things whatever under simulation is going on. Maybe some little bit little significant error will be there but can be ignored, such a little error of resultant concentration.
Okay, and probably in today's last talk, we will be listening from Krish Chakrabarti
Right.
from Duke University more about this commercialization, hopefully. So
Exactly.
thank you very much, madam, for such a nice introductory talk and also describing more about all these things. Thank you so much.
Okay, thank you all of you.
Okay, thank you, ma'am. So, can you please let me share my screen? Okay, okay, thank you.
Yes, yes.
Okay. So, ma'am, here from the university side, and a token of appreciation for you, and this is the
Thank you
memento
so
for
much,
you, ma'am.
sir.
So, thank you and sharing us this such nice field, introducing us. So, thank you so much, ma'am.
Thank you. Thank you, everyone.
So, we have our next